Hello and welcome to Genomics in the Cloud Book Club, Week 15. I'm your host, KT Picard. And today, the final installation of our book club will be discussing reproducibility. In chapter 14, how to make a fully reproducible paper. As usual, we'll have our usual additional resources and an open discussion at the end. So it's really a pleasure for me to introduce our 8th guest speaker. We conclude our book club with a review of best practices to create reproducible research. Today, we're honored to have with us the scientist whose work forms the basis for this chapter. Our speaker is a multilingual French-American scientist currently working at the Wellcome Center for Human Genetics at Oxford University. Previously, he was in Chile, where he taught programming and bioinformatics concepts, including Terra and Whittle, all in Spanish. He's earned his PhD in genetic medicine from the Institute of Genetic Medicine in Newcastle upon Tyne in the UK. A few years ago, one of his workshop proposals merged with one of the Broad's GITC workshops, and his PhD work became the case study for today's presentation. I am pleased to welcome back our guest speaker for our final meeting. Please welcome Dr. Mathieu Miosek.
Thank you, KT. I'm glad to be back in the driver's seat for this very special chapter. As you pointed out, it's not just any case study, it's a case study based on my research. So not only is it work I'm very familiar with, but it's also the creation of this chapter in some way intertwines with my own history. So I'm going to go ahead and share my first slide. Okay. Can everybody see the slide?
Looks great.
Okay. So in the previous chapters, we've kind of covered different concepts of doing genomics in the cloud, the analysis of Jupyter notebooks, how do you handle data in tables, how do you use the Google Cloud, and how do you use Terra. And we've seen in the last perhaps 2 or 3 chapters how to bring it all together. But now with this chapter, we're going to bring it all together again, but with an actual case study. So something entirely new, entirely originally outside of the Broad Institute. And this will be an opportunity not only to grapple with some of the challenges of reproducibility, but also show the power of Terra and making reproducible stuff in Terra. So I thought I'd start by how this all came about. There was this idea at the Broad Institute to have this case study as part of the GITC FireCloud workshops that the Broad Institute was giving. So just for context, FireCloud is, I think it's been mentioned before, but I'll mention it again, was the name of Terra a few years back. So back in 2018, FireCloud was, Terra was still called FireCloud, and now we have something brand new called Terra. So it's more like, it was sort of like a beta for Terra. And so they had, at the Broad Institute, they had this idea of creating this case study. Now, it so happens that one of the first workshops where they were going to present a case study, before they knew what it would be, was a workshop in Viña del Mar, Chile, for the ICB LA Soy Pollo 2018. And it also so happens that I was going to present a workshop there, although I have to say that when I postulated a workshop for for that event, I didn't really have that much of an idea, like exactly what I was going to present. So it was kind of like a nice accident, a nice serendipitous accident that the Broad Institute were presenting there. The organizers said the two groups are presenting stuff that kind of overlap in some way. So why don't you guys join forces? And I mean, for me, that was absolutely a fantastic opportunity. So of course I said yes. And luckily for me, the Broad Institute said yes. And we started collaborating on that. And we decided to turn one of my recently published in preprint form, one of my recent studies from my PhD, decided to turn that into the case study. despite all the difficulties, as you'll see, that entailed. So the Broad Institute were also presenting earlier in that year, that was in 2018, they were going to present earlier that year at the American Society of Human Genetics. And so we started working on this case study project immediately through weekly meetings. And then we were able to deliver for both of these workshops the case study. And this case study, so these two workshops are the ASHG 2018 in San Diego, USA, and then where I was not present, even though it was mentioned in the poster, and then the ISCB LA Soybio 2018, in which I was present. I've put a picture there. That's me presenting part of that workshop. And of course, you know, I don't want to give the impression that it was just me. Of course, I had an entire team of Brodies that I was working with. It was still very much a GATK workshop. So that was a 2-day event where we unveiled the case study towards the end of that 2-day workshop. This case study that ended up in the book in 2020 was also part of several other workshops in 2019. One interesting one towards the end of 2019, interesting because it happened at Newcastle University, so where I did my PhD. One of these workshops was presented to a number of people from my own team, some of which have worked on that research, so that nicely comes full circle. Now, the chapter that we're going to look at today is not hands-on, but it's a very instructive one. I think with one slide, I can illustrate why we're not going to be reproducing it ourselves, and more looking at how it was reproduced. It was quite the effort back then, and even now that it's all set up, it does involve a high cost and a high amount of hours. But we're lucky to be able to marvel at the sheer work that went into this, especially I have to say on Geraldine's part. Okay, so before I delve into some of the specifics of this study, I thought I would mention the difference between reproducibility of analysis against replicability of study findings. Now, in the book, they're very humble. They say, the book says, okay, this is our definition of reproducibility and replication, and this might vary and stuff. I think that's a little bit humble. I think essentially those are the correct definitions, and then when they get switched around, that can tend to be confusing. So if you have an original experiment, reproducibility is essentially running it through again, ideally. So that means you use the same data, the same methods, the same results. Okay, so reproducibility is just, does it work systematically? And if you've built something solid that you haven't been where you haven't been swapping around parts, that should happen. So reproducibility is just about saying what I did, if I run it again, do I get the same results with the same data and same methods? Replication, which is also very important in science, is where you will maybe have slightly different data. So say, for example, in an original experiment, you have microarray data, and in that case, you have sequencing data, but the problem is similar. Then you use orthogonal methods, so methods similar to your original study. Then you might produce some new results, but with that idea that you're going to replicate some of those findings. So that means that your results are either going to confirm or contradict that. So, for example, when you hear of studies where scientists say they've done something extraordinary, like created cold fusion, this will often be followed by no scientists have been able to replicate these findings. And that's because probably they're not replicable. So it's this idea that in science, we have to try, other teams have to try and recreate some of those results, maybe with their own methodology to confirm those results. And this is true of my own research as well. After I published that paper, there were different teams who found who found in tetralogy of fallow patients, for example, a tendency towards mutations in FLT4, which was one of the genes that we found. So that's So that in a way is an example of replication. But what we're trying to do here is reproducing. So trying to follow as strictly as possible what's been done in the paper. And this is going to be an opportunity, and here I quote the book because I can't put it better myself. It's an opportunity to evaluate the barriers to computational reproducibility of genomic methods as they are commonly applied to human medical genetics, and teach the audience to overcome these barriers. And I think that this chapter does exactly that. Okay, so before I go into what chapter 14 is really about, which is reproduction of data and how difficult it is, and what are the different strategies to get around certain difficulties. I thought I'd talk a little more in depth than the book does about the research that is at the center of that case study. So the research is on a particular congenital heart disease condition, which is called non-syndromic tetralogy of Fallot. This affects 3 out of 10,000 births. So whilst considered still rare, it does affect a certain amount of, a fair amount of births. Now, this disease has on itself a high mortality rate, and we'll see, and it'll become obvious why in a second. So without surgery, the mortality rate is in the first 10 years of life is 80%. So in many cases, a death sentence. Thankfully, in the last few decades, or last half century, I should say, we've been able to repair a lot of that damage caused by tetralogy of Fallot with very early surgery right after birth, typically. And the survival in the first 30 years of life is now something closer to 85%. Okay, so it's highly repairable. It's obviously a very complex surgery, but it's one that has a high rate of success. Of course, that will also tend to depend where the patient is situated geographically, but on average, it has a high survival rate, which has implications for future generations as well. So tetralogy of Fallot, as its name indicates, is 4 cardiac malformations. You have what's called a large ventricular septal defect, so that will mean, in common parlance, that's a hole in the heart. So you can see that the 2 chambers that are supposed to be separate are now communicating, and that means that oxygenated, non-oxygenated blood is mixing. So that's already one bad thing. But on top of that, you have a displacement of the aorta. That's this part here. You can see that it communicates with both chambers. Again, really not ideal. Then you have a narrowing of the pulmonary valve, which means that the blood has a hard time circulating through here to get to other parts of the body. And then as a result of all the work that goes into pumping the blood because of the altered circulation, you have this muscle here that becomes thicker and thicker because of the sheer effort in pumping the blood, and you get a progressive right ventricular hypertrophy. So that's a phenotype that gets worse with time. You get a thicker and thicker heart muscle. So you can see from here that it's a very complex disease, and it's understandable that it has a high mortality rate if it's not fixed by surgery. And this duality between without surgery, death is at 80%, but with surgery, there's a survival is at 85%. This has some strong genetic implications, because it means that up until recently, when you had this kind of diseases, you tended to die off pretty early, which would suggest that if there's any genetic predisposition to it, they will decrease genetic fitness quite strongly. So you wouldn't expect common variants to have much of an effect on this disease, and you would expect to find this disease caused by rare, often de novo, high impact mutations. Typically that means mutations that have appeared in a single generation that is not present in parents, or may perhaps present in 1 or 2 generations, but specific to one family cohort, thanks to advances in surgery. So that was our prevailing hypothesis. And this is also why as you'll see later in the analysis, we focus on looking at genes rather than variants. And this is a preface for the difficulty in reproduction, because since we are dealing with patients with a rare disease, and we're looking for rare variants, we need a lot of patients. So that means something like 867 patients originally, with 1,200 cases. It was brought down to 829 because of issues with blood samples, as is common in science. But that means we're dealing with not only a lot of samples from a lot of different countries, we're dealing with a lot of different researchers from a lot of different centers. So as you can imagine, the data inevitably is going to be controlled very tightly. You're not going to have an open access situation, which immediately sets roadblocks for total and complete reproduction, as we will see. And that also means there's a lot of authors involved. There's a lot of people involved in the process. And this is therefore why we end up with a situation, as pointed out early in the chapter, where someone like me, you can see that little me character, that's literally me in this case. I have access to the data. Well, I had access back to the data back when I was at Newcastle University. I had the stuff running on my computer, and I could see all the results, even those which inevitably, as happens in research, don't get necessarily published. And then what you, on the other hand, have is the results in paper form or preprint form, which just gives you the important, what we consider the important results, and and when it comes to data, you may not have access to data at all. So with many of these research projects, this data is, as the saying goes, available upon request, which often means it's not available. In fact, there's two situations here in which our paper has been in. Originally, when this case study was conceived, the research was actually in preprint form. So that data didn't exist anywhere online. So that was a first. The data was really literally locked away locally. Then when it was published as a paper in November, then that data became available online, but you still have to ask access for it, and you still have to make a reasonable request as to why you want access to that data. For myself, it's easier to get access to that data, and I have gotten access to that data to continue working on that project, but it might be more difficult for somebody else to get access to that data. So that's two levels at which you as the user might not get access to the data. Then there's the problem of the processing and analysis pipeline. I think this is going to get better as time goes by. Right now, with our study, we didn't use GitHub, we didn't use Docker. Those were kind of early days for using those things, but now it's kind of expected that you're going to, if you're going to create a new analysis pipeline, you're going to put it on GitHub and perhaps on Docker. I think probably GitHub is more likely than, well, the book points out that you have to be extremely lucky for it to be on Docker. And that leaves the paper, which, as I mentioned, has some of the results, but it doesn't show you absolutely everything. Not by some sort of, because researchers are trying to hide stuff, but the paper has to be readable, so you can't show each and every single result. So that's the situation in which we find ourselves with a lot of research, and this particular study is not that different. So if we look at a survey of what we have here in this study, this is essentially what can be gathered from the paper. And as the book suggests, certain things are a bit too vague to reproduce exactly. So for example, this MUGKIC, GenPipes DNA sec, they mention a number of tools and the versions, but you can't be exactly sure what they will run with, what parameters were used. So there has to be some amount of guesswork that goes into this. And obviously being involved in this, I was able to help to a certain extent, but there's also a limit to, since this was a global collaboration, there was also some things that I was myself in the dark, and I couldn't necessarily help out. Some later stages in the analysis, I have much more of a grip on that, and I was able to, for example, translate Bash and Perl scripts, or we were able to translate those into something that could run on a Jupyter Notebook in R. So the first step of what Geraldine and her team did, and she really gets credit for this this section, because I remember distinctly her putting a superhuman amount of effort into getting this synthetic data to work. So I mean, in the book, it's already pretty clear that this was a difficult task to do, but believe me, it was even harder than the book suggests. It was a work of months, so that was quite impressive. So here, there's two things to take into account in designing a reproducible implementation. What the team wants to do is not just try and create something that's that's close to the original data that's restricted as possible, but also the final product itself has to be reproducible. So if you can't get full reproducibility of a piece of research, you can at least the copy of it, the synthetic data version of it, can be open source and reproducible. So this is why the team went back to this author called this paper by GITC and al, which talks about reproducible research and the steps that you have to look at in terms of data input, in terms of process, in terms of analysis. And so all these decisions were made, taking that into account, making sure that what we ended up with was FAIR. And FAIR stands for findable, accessible, interruptible, and reusable. And as you've probably seen from looking at the tetralogy file cases workspace in Terra, is that it fulfills all these requirements, even though the original research doesn't. So the journey began with creating synthetic data. Originally, the plan was to take the 1,000 genomes directly and spike them with notch 1 variants. This didn't pan out because at the time, 1,000 genomes, the data that was available was low coverage data, which just didn't really work for that purpose. So what ended up happening is VCF files from the high coverage data were extracted, and they were then applied to synthetic data in order to create individual BAM files. So the idea again here is you create synthetic data. That synthetic data is based on the reference, so the reference genome, and then you go ahead and just throw in a bunch of variants, maybe some mutations and some errors to try and create as lifelike a version of real BAM files. And this was done using this tool called NetGenReads. And what's interesting about that tool actually is that someone I actually did my bioinformatics master's with is a co-author of that. So bioinformatics is a small world. So this, as mentioned in the book, this involved a lot of wrangling with the data, fixing headers, and separating the VCF data into a format that made sense. So in the book, they mention how all the 1,000 genome samples are pulled into a single VCF separated per chromosome. So you have several VCFs, but they're per chromosome VCFs, when what they needed was single VCFs with all the chromosomes. So by individual instead of by chromosome. Okay, so to just show the sheer work that entails, I'm going to go to the workspace. If we go into workflow and look at this first step, collect 1,000 genome participants and you go into script, you can see the amount of work. And you can see there's a lot of interesting notes here about what they had to basically give up on. For example, chromosome Y is completely left out because it's just too problematic. And then chromosome X has to be processed separately. So if you have a look here, you'll see that for each chromosome, here represented by contig, you're running this retrieve and sort, and then you are running consolidate. So essentially, once you have all the chromosomes together, you can put them together. Yeah. So and as you can see, within a single task, retrieve and sort, you actually have a lot of things going on there. They mentioned that the header just didn't work with the implementation of NetGen read, so they had to change that. Then they had to select the variants, so that meant getting certain intervals and getting the specific participant they were interested in creating a VCF for, and sorry, not a VCF, a BAM file for, and then, oh no, yes, a VCF for, sorry, and then sorting the final result for that. And then that's the consolidation step to put everything together. So that's a little more, a little smaller, just merging the VCFs and then indexing. And then that's it. And I say that's it, but that was a phenomenal amount of work on Geraldine and her team's part. So just to avoid confusion again, really insist on this point. There's actually 2 steps here. There's actually 3 steps. The first being what we just saw, retrieving the 1,000 genomes and turning them into something that we can use more easily, and then generating those synthetic BAM files and spiking them with common and rare variants in order for them to look like actual patients. And then there's a 3rd step where we are going to not spike data from entire VCS, but just add in specific mutations. Those are the mutations of interest from the preprint. So you put the preprint here. There's in the supplemental materials, you can find a list of the Notch1 variants, not necessarily all causative of the disease, but definitely in a bigger number than we would expect for that particular gene. And so we put those in a bed file along with neutral variants to avoid batch effects, which is mentioned a little later in the book. And then that gives us synthetic data that has Notch1 variants and neutral variants added to them. So in a little more detail, this is what it will look like with NetGen reads. You start with synthetic data that's based on the reference genome, to which you are going to add homozygous and heterozygous variants based on those 1,000 genomes data. And then once you've done that, you're going to do the remapping step again. Why do the remapping step again? Because you want to simulate the fact that, for example, the mapping might come out slightly wrong because of the existence of those mutations. There's always the risk when you're aligning something that doesn't align quite like it's supposed to. And if your goal is to make your synthetic data the most like possible, that was going to involve realigning those and getting some aligned BAM files that look as real as possible. And then the second separate step is using BAM searching, where you essentially just pick particular locations where you're supposed to have a Notch1 variant and add them to specific files. So for example, the first data set that was run was 100 patients. 8 patients were spiked for the Notch1 variant. And then for the cohort that has 500 patients, we added 49 Notch1 variants. So here's another important thing to mention, which is that not all patients, because of what we're looking at, not all patients with tetralogy of Fallot are going to have a Notch1 mutation or a non-synonymous predicted deleterious Notch1 variant, which means that not every patient in our synthetic data set that's not received Notch1, not all of them are controls. Some of them are still cases. They're just cases where we don't see Notch1 appear, just like the original data. It's important to say that in our original data, we saw an excess of Notch1 variants, but not in all 827 patients. We just saw them in a couple of them, but it was enough of a set to qualify as significant. So before I move into the analysis phase, I just want to again show in the workflow section what that looks like. So again, they mentioned in quite a lot of detail in the chapter that this also caused a number of issues. You'll see that fix VCF header appears a second time, and they also have to add read groups and other such things, and so it takes it took quite some effort, and you can see like that they have thrown in the occasional awk command to do something quickly. I personally think that's great. I do this all the time. I'm always using awk or grep to do stuff as quickly as possible, rather than using the tools, the established tools in bioinformatics. It's a little bit it's a bit lazy at times, but it works. It works great. And then there's this final step in the processing, which is BAM surgeon. And as you can see, as mentioned in the book, you can just tell from looking at how short it is in comparison to what we've seen, that they've had much less problems with those. If you look at which one is that? Okay, the add SNV task, which is the main BAM surgeon task. They're adding the variants in here, and then once that's done, they're just sorting and indexing using the typical sort SAM tool. So nothing particularly special happening here, just sorting and indexing, and all the magic is happening in this previous task. And we just have these two tasks, each running just one command essentially, and with that, they're done with the processing. So that's the processing stage. As mentioned in the book, they make this distinction early on between processing and analysis, the processing being more of the computational intensive side, and then the analysis being what's quite specific to this particular study. So when we finish the processing stage, we have a large list of what I call deviations, but to make it more understandable, we can just call them variations from the reference genome. Some of those are actual bona fide variants, some of those are errors, and so we have to find a way to separate those, and not just separate variants from errors, but also separate variants that we frankly don't care about, like common variants and synonymous variants, against those that we do care about, which are those that are predicted deleterious, those that are extremely rare. So this is what SNP-F and Gemini do. SNP-F predicts the deleteriousness of particular variants based on, for example, the protein conformation that it will have, or whether the change leads to a synonymous amino acid or whether it doesn't. And then based on that, we can start filtering out variants of interest versus variants not of interest. Of course, it's not a perfect, it's not perfect. It uses heuristics, so you will have a number of false positives in there. Then tools like 1000 Genomes and EXAC, these kind of databases, now you would use GNOMAD, but these databases are used to filter out anything that's common. So anything that's above 1% just gets stripped out of the data. We want to only focus on what's rare, okay? And this is where our control set becomes useful as well, because we want to filter out anything that appears commonly in that control set as well. So this is true both of the real data and the synthetic data. We're just going to cut out anything that appears in both sets. We just want stuff that appears in the cases, not the controls. And then once we've done that, the last two steps are done in the Jupyter notebook, because this is something that's where we want a little bit of modularity, maybe a little bit of flexibility, both when we're doing the real study and when we're looking to recreate it. We want to be able to control our output and how that finally looks. So we use this metric called CADD, which is the output of Gemini, and is a rank for our variance based on deleteriousness and other metrics. And then we have this final DOED statistic that I will explain in a second. I just wanted to show what that looks like finally. So that's the last step here. You'll notice that I've kind of skipped over these two because by now we're quite familiar with them. There is this one slightly modified because we use hard filter, even though that's not best practices. I mean, unfortunately, those things happen. And here we have this final step where we're going to first run SNP-F. As you can see, here's SNP-F annotation, and then create a database for Gemini and start querying that database, which means we're going to annotate our variants, add more information, and then based on that, filter out some variants and then rank others. Okay. So yeah, so you see this, we have a task for annotation. So, you know, in the interest of time, I'm not going to go into too much detail, but this is essentially the final workflow. After that, we move to the notebook. So this filtering step of filtering for anything that's smaller than, filtering out everything that's smaller than, has a small score than 20, is done in this notebook. So if we go to here, we have some setup. I think probably now in 2021, a lot of this setup is not necessary anymore. This is back when we were in FireCloud and it was harder to set things up. I think now things would be much easier to set up. So if we go straight to the filtering step, I don't know if anybody's familiar with R, but this is like R code. And here essentially what we're doing is that we're filtering the data for anything that's has a score of over 20. So again, Gemini ranks variance and we just select anything that's over 20. Then what we've done, and I'm going to show that in the slides, is we have look at within a certain gene of a certain length, how many variants we observe. So if you take an average of all the genes and all the genes, you can get a good idea of how many variants you expect to see in a particular gene. So for 100 base pairs, I expect, or let's say for 1,000 base pairs, I expect to see maybe 1 or 2 variants, okay, based on the entirety of the data, using as taking into account our assumption that most of our data is going to be just regular genes with regular variants that are not causative. Okay, so based on that, we can get an average of how many variants we expect for a gene of a certain length, and then do a test whether we're seeing an excess in any genes. Okay, again, this is something that's a little hard to wrap one's mind around at first, because the idea might think, okay, well, we did all this filtering for predicted deleterious, can't we just pick out specific variants, say, okay, I've got a variant in notch 1, so that must be causative. And the fact is there's a lot of false positives, and so you're not going to be able to do that. And so a proxy is to look at the gene and see if you have in the cases a lot more variants than you would expect in a particular gene than in all your other genes. And this is what happened with notch 1. This is what happened with another gene called FLT4. For the purposes of reproducing the study, the team decided to focus on notch one because that was the one that had the bigger signal. And so what we should be able to see looking at variant load is an excess of variance in notch one. And just for comparison, just so that you can see that the Broad Institute puts a lot of effort into making their graphs look really nice. This is what the graph looked like in 2018 when I made it myself. So it's a lot less it's a lot less nice looking. I thought I'd put that in there just as a comparison. There's no need to read the slide or anything, but yes, this is what it looks like in the book, and it's much nicer. So once you've looked at excess of variance using Poisson distribution, what you end up with, depending on how many samples you looked at, is something like this. And this is actually quite a nice reflection of what you find in the original paper, that you find this notch one signal that's towering over everything else. When you look at only 100 samples, you'll see that the gene for obscurin kind of overpowers that. So artifacts, if you don't have enough statistical power, artifacts can overpower your actual signal. But once you get 500 samples, you've got a nice signal. So that shows, in addition to showing an example of reproducibility, this is a good example of the importance of statistical power, of having more samples, and those samples giving you more powers and therefore getting a stronger signal. Which is why, in effect, in the original study, there's 829 patients against 1,200 controls. This idea that if you're going to look for rare variants and you're not going to be able to pick them out, you're not going to be able to pick out single variants, but you're going to have to find the signal in the noise, the signal in this particular gene, you're going to have a lot of power. And this is indeed what happened in the original study, and this is how it was reproduced with the synthetic data set. I think that in the Jupyter Notebook, the Jupyter Notebook's been run, so you'll be able to see what it looks like within here. Again, I'm not going to go, you're welcome to read. I think it's a good idea to read kind of what we've written for the Jupyter Notebook, but I figure a lot of people are maybe not familiar with R. So, and in the interest of time, I won't go into too much details, but this is essentially what you end up with. So these are from the preprint. Well, they might actually be from the final paper, but either way, you can see that notch one is towering over the other genes, and this is essentially what you see in the example of 500 participants. We did have obscurin here, but then when we have 500 participants, obscurin gets relegated to a lower rank, and what we see is we have a frank excess of variance in notch one, which again means not every single one of those variants that we found are causative of tetralogy of Fallot, but at least some of them will be. And because we're finding so many, this is evidence that notch one mutations are very important for the development of tetralogy of Fallot. And that was the result that we found. As the book points out, I think quite early on, our finding really isn't that we found that this gene is related to tetralogy of Fallot, because that was found in family cases. It really is that we've shown that it's an important one, that it's amongst the genes that are causative for tetralogy of Fallot, notch one is one of the top ones. Okay, so got 15 more minutes, so I'll try to wrap up. The final thing that I wanted to focus on was this last section, which was about the long winding road to fairness. Again, fairness standing for, I think it was findability, accessibility, interoperability, and reusability. And so here are some, after kind of some reflection about how this case study went, some indicators for the user, that means us, how we can achieve computational reproducibility and fairness in our work. So the first one, and I think this one, it's worth mentioning, but I think it's for most of us is very an obvious one, is to keep it open source. Thankfully, bioinformatics is a field where maybe like 90% of the tools or at least the ones I've come across, are open source. So GITK is open source, SAM tools is open source, Abed tools is open source. A lot of the stuff that we use is open source, and we should keep it that way. Version control is very important, and here Terra can be very useful because it forces versioning either through GitHub or Dockstore or within its internal method repository. You can't get away with not versioning. Automation and portability. So that's a call for using domain-specific languages like WDL or CWL or others, instead of using very intricate Bash, Python, and R scripts as we would usually have done back when we were building our analysis locally. And indeed, in the research that I and others carried out at Newcastle University and Manchester University, we very much used Bash scripts and in our case, Perl scripts and some R scripts to run this entire pipeline. Here, the idea is actually provide a pipeline for your workflow that just brings everything together the way we've seen it across various chapters. And then built-in documentation is important. And here, Jupyter Notebook creates an environment in which this is made easier. I've said before that Jupyter Notebooks are a great resource for teaching and learning different languages, whether it be Python or R. And as a consequence of that, they're also great for documenting the logic of various steps, right? You're able to say, this step does a specific thing. This is what we expect. This is the priors that we've used in choosing why we do the steps. So Jupyter Notebook makes it easier for you, so be explicit. And then the final, and perhaps actually the hardest one, but one that hopefully some platform like Terra will bring about, the importance of open data. So we're referring to open data as much as possible. But if that's not possible, if, for example, the data is restricted because it's a huge collaboration or there's some concerns about security, encouraging the researchers to create something using open access data that's similar to the original data in order to demonstrate their analysis, and failing that, doing what was done for this chapter, which is using synthetic data. So either of those to demonstrate the analysis and how it's supposed to work, to convince other researchers of how it's done, to give them the opportunity to use the same techniques as well. It could be interesting, say, for example, if I have reproduced the pipeline for tetralogy of follows, somebody with another condition with some similar assumptions might say, hey, I can use this particular workflow for my data, and therefore do something that's not reproducibility or replication, but is a reproducibility of methods. So that could be potentially interesting. I'm just going to just illustrate that built-in documentation point by showing again this Jupyter Notebooks. As you can see, it was very well documented. So we explain not only the choices that have been made, but also what we expect to see. Is it what we expect? Is it what we ended up seeing? And what, for example, one example was earlier. Here we have names of different variables. We explain what those variables mean essentially, in order to guide people. Even someone who's not familiar with R can get a feel for what's happening in this code. So once again, keeping it open source, version control, automation and portability, built-in documentation, open data. This is what we should all be striving for in our research. Okay, and with that, I have some additional resources. These have been added by Katie, so thank you for that. I thought that in addition to that, I would add a few more additional resources, more as historical interest, which are other places where this case study has been mentioned. So the workshop in Viña del Mar, of course, those are outdated slides, so don't necessarily use that, like just with the caveat that they're that they're a little bit outdated, but you have posters about this case study. It's propped up, it appeared in different places before it appeared in the book. There's some recorded presentations that deal especially with the case study. I've picked one in particular. There's several, but they're all quite similar. And then of course there's this book, I don't know if you've heard of it, called Genomics in the Cloud, that came out last year, that talks about it in its last chapter. So it's definitely worth the read through. And that's it for me. I'll pass over to Katie. I don't know if you. I'll just leave the slide up and you can do. Yeah.
That's great, Mathieu. Thank you so much for this presentation. I really, it's a nice capstone to this entire journey. Thank you for being with us and sharing your experience. And also with us on the call is Geraldine, one of the authors of the book. I wanted to give her just a few minutes to talk about this process before we tie things up. The way that you two worked together was incredible. I really enjoyed this chapter. Geraldine, would you like to say a few words about what you learned from this process?
Oh, sure. I mean, the process of reproducing the work, I think, you know, initially when we started out, I thought it was going to be easier than it ended up being. We kind of knew that the data access was going to be a component, but I had not. Once we kind of designed the strategy for making synthetic data, it felt like we had a good strategy. I did not expect how much additional data wrangling we'd have to do with the 1,000 genome stuff, the amount of testing and realizing, you know, the headers were not strictly adhering to spec. So some of the tools are very lenient, and so you could get to a certain point and then you'd hit a wall because GITC is extremely stringent by default on many of the requirements, specification requirements. The thing is, every time we ran into one of those problems, it was kind of justified. There was a good reason for needing those headers to be correctly formatted and so on, because there's various pieces of information that the tools require at certain steps. And so I would say that to me was one of the first times I experienced through an end-to-end project all of those issues that I had been helping people with on the GITK forum for some time, because my job at the time was to help people through those kinds of issues, but I always had it in a piecemeal. People would come with a specific step and I would help them pass that. And so doing this project was kind of a rare opportunity for me to experience the full amount of frustration and little issues that just delay you and so on. And so from that point of view, it was really interesting, painful, but really interesting. And I learned a lot. And I tried to, when we wrote up the chapter, I tried to kind of convey some of that, hopefully not in a discouraging way, but like it's normal to run into these kinds of things, and there are ways to get past, and there's always a way through. But then from the perspective of like, how do we make things reproducible? I think it was especially interesting to figure out like, what are the approaches that we can take, and how can the tooling, some of the more recent tooling, really help us so that when we're publishing a resource, other people are going to be able to use things more out of the box and a lot less, with hopefully a lot less of this frustrating work. And my pitch to authors, to people who are publishing their research, is really think about your paper not just as like the write-up of your work, but a jumping off point for somebody else. Somebody else hopefully is going to read your work, is going to be interested in reusing some elements of that. That is a good thing. That can lead to citations for you. That's good. That's currency in the academic world. but you have to make it so that it's not like people don't feel like they're hitting a brick wall. If you make it so that people can reuse your work, use it as a jumping off point, they will talk about your work, they will cite you, it's good for you, and it's good for the field in general, because the more we can work together to eliminate these unnecessary hurdles, the faster we can all move forward. And really, from the point of view of research as a team sport, adopting these kinds of principles can be very helpful and beneficial for all of us. So I hope that helps. But in general, I will say working with Mathieu on this case study was a wonderful experience. It was a very cool collaboration, very serendipitous in how it arose, and I think it's been wonderful. And Mathieu, I caught most of your presentation today, and it was so neat to see the story told, especially in your words. So thank you for coming on to do that. It was very cool.
You're welcome, and I'll add that for me, even though I had read like a couple of drafts of this chapter just to read through it from start to finish and stuff, and just the memories of our collaboration that I brought back, it was absolutely fantastic. And yeah, and it was funny to me. I mentioned it briefly. It was funny to me to see how like what my graphs looked like back in 2018 and how neatly those have been changed into something like much more edible. So yeah, no, it was a absolutely fantastic collaboration. Obviously, I feel like I benefited immensely from that collaboration. So I'm happy that happened. It was very unexpected.
It was, but I think it's really yeah, what came out of it, I really hope. Not only was it fun, I think for us it was useful, but I hope it's useful for more people. And I really treasure that collaboration, and we should do something again. That was a lot of fun.
Definitely.
Well, I'd like to thank both of you for, again, a fantastic way to wrap up our book club. I thanks everyone for joining us on this journey. A special thanks to our presenters, to all of our members who have made such a great contribution over the last 3 months, over 4 months. And also a special thanks to Dr. Geraldine van der Ora for being with us here, answering our questions, patiently walking us through as we've learned this material. So that's it for the Genomics in the Cloud Book Club. Again, thanks for this fantastic journey, and we'll see you again next time. Bye-bye.